How's everybody doing? Can you guys hear me and see my screen? Cool. So this week you guys have an exam coming up on Friday. So I can either try to split my time pretty evenly between this worksheet and the exam review, or I can concentrate on knocking out the worksheet and then just whatever time is left over, leave for the exam review. What do you people want to do? What do you guys want to do? Cool. So I will try to burn through this guy as fast as possible then. So find the fourth derivative. Polynomials, if they have a power less than whatever the number derivative it is, are going to disappear. So for example, this guy goes 4x squared to 8x to 8 to 0. So it just disappears to 0, and that happens on the third derivative. You'll find that the same thing happens for this guy on the second, and the same thing on this one for the fourth. So this guy is actually just going to be -2 times 4, which we get from the first derivative, times 3, which we get from the second derivative, times 2, which we get from the third derivative, times 1, which we get from the last derivative. So that is -48. Does that make sense, people? Cool. So they were nice enough to give us the inflection points for this guy. So now all we have to do is check where is it concave up and where is it concave down. So that's the same thing as asking, concave up means that the derivative is increasing. Concave down means that the derivative is decreasing. It's not to say that the derivative is positive or negative, to say that it's increasing or decreasing. So we're looking at the double derivative, the second derivative, to see if that's increasing or decreasing. And if I check over here, okay, so my slope is positive. The slope is steep right here, and then it's not that steep over here, it's very mild. So that tells me that the slope decreased, and then it turned negative. So from negative infinity to -2, it's getting steeper and steeper all the way till I hit -2, it is concave down. And then it's going to be concave up in this next region, because here, okay, it's steeply decreasing, but less and less steeply decreasing. And then, wow, suddenly it's increasing. It's going up, faster and faster. So that tells me that from -2 to 6, it is concave up. And then from 6 on to infinity, hey, it's very steeply increasing, less steeply increasing. Suddenly it's decreasing. It's going to be concave down again from 6 to infinity. Does that make sense to everybody? It's an important concept. Good. Okay, we're going to do the same basic idea with looking at these two pictures. Hey, it's decreasing pretty mildly over here. The slope is negative, but it's not that steep over here. But then when I get over here, it's becoming really, really steep. So it tells me that the slope is decreasing as I go from -infinity to 2. So it's concave down. And then we get the same thing actually over here, right? So it's very steep, and then very mild over here. So what's happening there? Actually, so we have the opposite thing. It's very, very steep, very steep. This whole time, the slope is negative, but it's going from a very big, in square quotes, negative number to a very small, in square quotes, negative number. And that means that it is concave upwards, right? From 2 to infinity. Does that make sense to people? And here there are no points of inflection because it's not defined at 2, which is the point where it switches from concave up to concave down, or the value at which it switches. It's not actually defined at that point. Here, again, at the point where it switches is not defined, but we're going from steeply decreasing to steeply increasing. So that tells me that it is concave up from negative infinity to 0, right? And then it's switching from swiftly increasing over here to decreasing over here. So it is concave down from 0 to infinity. Again, no inflection point because because it is not defined at the point at which it switches. Okay, so now when I'm dealing with the actual algebraic structure instead of the graph, I just do the second derivative. So here I do f double prime of x is going to be equal to negative 3 times 2 times x minus 12. And then I want any points of inflection are just going to be where this double derivative is equal to 0. So I'm going to set that double derivative equal to 0. And then if I rearrange this, I get 6x is equal to negative 12. And then if I divide by 6, I get x is equal to negative 2. So when x is equal to negative 2, that is the potential point of inflection. It's not guaranteed to be a point of inflection, but it's a potential point of inflection. So now I just do, I check the 2 intervals on either side. -2 to infinity. And now I just plug in a test point on either bound. What do people think I should pick as a test point? What is the standard rule? If possible, you always pick this thing as a test point?
0.
Exactly. Thank you, guys. So if I plug in 0 here into this equation, into this equation to see if I get something that's positive or negative, I get negative 12, right? So f double prime of 0 is equal to negative 12. So that tells me that this section is going to be negative. And then I'll just pick, say, 10, a negative 10 on the other one. So f double prime of negative 10 is going to be equal to positive 60, because we have negative 6 times negative 10 minus 12 is equal to 48, and that is going to be positive. So it is concave up from negative infinity to negative 2, and concave down from negative 2 to infinity. That makes sense to everybody? Cool. So here, again, same basic idea. We do the double derivative, and then we get f double prime of x is going to be equal to, we get 6x squared plus 6x minus 12. And then we set this guy equal to 0 to find the potential points of inflection. I'm just going to factor out a 6 from this whole thing. So I get 6 times x squared plus 6, plus x minus 2 is equal to 0. And that's 6 times x plus 2 times x minus 1 is equal to 0. That's x is equal to 1 and x is equal to -2 are my 2 potential points of inflection. So now I just break up the region into -infinity to -2, -2 to 1, and 1 to infinity. If you just plug in these values, you will get that this guy is negative and that these two guys are positive. Right, yeah. So you guys can check that yourselves, but I won't do that just to save some time. So that tells me that we have the 2 points of inflection at x equals -2, f of -2, -2, f of -2, and 1, f, comma, f negative, comma, f of 1. And then we also get its concave down, or sorry, concave up in this region, union this region, and concave down in this region. So on to 3. For each function, apply a second derivative test to find the relative extrema. So if I do the second derivative of this guy, then I get, so what do I get? I get 2 times 3 times 2x minus 4 times 2. So the second derivative of x is going to be equal to this, and that is equal to 12x minus 8, right? And 12x minus 8 is, so I then set this guy equal to 0, and I get that it happens at 4/3. X equals 4/3, right? So now, wait, is it 4/3 or is it 3/4? So if I do 12x is equal to 8, and then I divide by 8, it is, sorry, it is 2/3. No, 4/3, why is it? I think I'm messing something up here, but I'm not sure what. But the answer key says 4/3. I remember getting 4/3 before. I'm getting 2/3 right now. Do people see what I'm doing wrong? So we get 2 times, that's 12, right? And then 8, so minus 8, and I get x is equal to 8 over 12. That's equal to 2/3. Whatever. I'm just going to pick 2 points that are on either side anyways. So what I would get negative, oh, sorry. I forgot to do the first derivative. So the first derivative of this guy is going to be equal to f prime of x. Sorry, I'm just going to restart this. So the first derivative, what is the second derivative test? What is the point of the second derivative test? Hint, it says it right here. So find relative extrema. Relative extrema can only occur at critical points, so where the derivative is equal to 0, or where the what's it called? It can only occur or at the bounds of where things are defined. This is on the whole real line, so it can only be the critical points. So I need to find the first derivative, set that equal to 0, see what's going on there. So when I do that, I get 6x squared minus 8x, right? So now if I factor this guy out, this is x, 6x minus 4. Sorry, I'm going to pull the 2 out of both of these guys. 3, so 2, pull 2x out of both of them. And this is where you get x is equal to 0 and x is equal to 4 over 3. This is where you get the 4 over 3, not the second derivative. Now I look at the double derivative of this. So that gives me 12x minus 8. So now, in order to check if these guys are maxes or mins, or potentially unknown, if I get the double derivative is equal to 0, I don't know what's happening. Now I just plug in these two values into this, and that'll tell me if it's concave up or concave down at the critical point, which tells me if it's going to be a max or a min. So if I plug in f double prime of 0, that is going to be equal to -8. And if I do f double prime of 4/3, that is going to be equal to 16 minus 8 is equal to 8. So that tells me that the double derivative, or it's concave up, where at 4/3, where it's concave up, it's a little bit, it's the opposite of your intuition, or it's the opposite of my intuition, but it is a min. And when it's concave down, it is a max, because it's switching from increasing to decreasing or decreasing to increasing. So that tells me local min, relative min, at 4/3, f of 4/3, relative max at 0, f of 0. Does that make sense to everybody? Cool. So if you were to do this guy, the derivative of this guy, this is one where you actually don't know. The second derivative test doesn't determine the value for you. It's going to be a minimum, but you tell that just by like picturing the graph. This basically looks like a parabola, basically like a parabola to the 4th power. So the derivative of this guy is going to be 4 times x plus 3 cubed. This only has mins at x equal to -3. That occurs 3 times. And if I do the second derivative, double prime of x, it equals 12x plus 3 squared. And so that is x is equal to -3 again. Does that make sense? So when you plug in -3 into this, you get f double prime of -3 is equal to 0. And that doesn't tell you if it's positive or negative. You just look at the graph, and this is pretty clearly positive. You can also, for x cubed, the point is going to be neither a max or min, and then -x to the 4th is a good example of it being a max instead of a min. So this is a min, but the second derivative test does not tell you that. So when an object is dropped straight down, the distance in feet that is traveled in t seconds is given by -16 t squared. So to find the velocity after 5 seconds, I have to do the first derivative. That's going to be equal to -32 t. And if I do s prime of 5, that's going to be equal to 160, -160. So that is the speed at 5 seconds after dropping. And then if I do the double derivative with respect to t, it gives me -32. This isn't t respective, so s prime of 5 is also going to be equal to -32. Okay, so find the absolute max and min of these guys. So this has an absolute min at x equals, or at x of 1, and it has local maxes and local mins at x, 2, and 3. So the absolute min can only be at either an endpoint or a local max or min. It happens that x1 is actually the lowest of all the values, but x2 is not the highest of the values because this guy's higher and this guy's higher and this guy over here is higher. So there's no absolute max, but there is an absolute min at x1, f of x1. Cool. Something similar is happening here, but we have endpoints and we have a closed bound and it's continuous. You continuous on closed bound, you are guaranteed to have at least one max and min. absolute max and min. So here, pretty clearly, absolute max at x1, f of x1, right? Then looks like my absolute min is going to be at x2, f of x2. But because that is lower than your other local min, which is x4. Is that what is called an open interval in the first example? Yeah, so that is a given, that is a given, or that is an open interval. Another open interval, it could be, so if these guys were just hollowed out. So actually, strictly what I should have said is closed and bounded, because the entire real line is technically closed. But if these guys were open circles instead of the filled in holes, so if you have something like this, there's actually no absolute max and min on this bound, because no matter how close, no matter how high you get, you can always get closer to the end. But if you fill in these holes, if you were to have this instead, then there is an absolute max and min, and it's just those points where it's defined. Does that make sense?
Yes, thank you.
Cool. And what I meant by bounded is that it has like finite endpoints. I will only do D and E here. Actually, I'll do C and E here to save some time. So it can only occur at critical points on the endpoints. So I'm going to do the first derivative to check what the critical points are within these bounds, and then I'll do the endpoints, and I'll also have to check the endpoints. So if prime of this guy is going to be equal to 8x to the 7 minus 4 times 32. I'm pretty sure it's 256. Sorry, no, it's 128. X cubed. And if I factor this out, that's going to be equal to 8x cubed times x to the 4 minus 16. So I get this guy at x equals 0, and then this guy at x is equal to 2, and x is equal to -2. This guy is not in my bounds, so I can ignore him completely. This guy, I already had to check because he's one of my endpoints, so he's not that interesting, but he is still a point that I have to check. So now I just have to do f of -1, f of 0, and f of 2 to check. I just plug these guys in. Whatever is my highest and whatever is my lowest are my absolute max and mins on this interval. So if I plug in -1, that gives me 1 minus 32 plus 2 is going to be equal to -29. So we get -29 here. If I plug in 0, I get 2. And if I plug in 2, I get, this is 256 right here. This is also 256. So they cancel and I get 2 again. So these guys are tied for my absolute max, and then this guy is my absolute min. Does that make sense? You're allowed to have 2 absolutes if they are the same. Cool. And then if I do the derivative of this guy, so this has no endpoints. This is another example of an open interval. It's just 0 to infinity. It has no endpoints. And if I were to do the derivative of this, I would get f prime of x is equal to 2, minus 16x to the -3. So if I rearrange this guy, I get, so I want to set this equal to 0, right? And I get 2x cubed is equal to 16. And then I divide both sides and factor, I get x is equal to 2. So this is my only potential critical point. And then there's a few different ways I can go about solving this. I can do the second derivative test if you want to do that, or you can check on either side of it, plug in on either side. I guess we should probably just do the second derivative test for the sake of relating to other stuff that we've done. So that will be f of x is going to be equal to negative, that becomes, sorry, positive 48 x to the negative 4. So if I do f double prime of 2, that gives me positive 48 over 2 to the 4. And that's not 24, that's 2 to the 4. But that's positive, which is the only thing that matters, which tells me that it's going to be a local min. So this guy is, yeah, so this is a local min. Or sorry, absolute min. Min at 2f of 2. Does that make sense to everybody? Okay. Do people have any other concrete question that they want me to answer in this section? If not, I'm going to switch over to the exam review. Okay, cool. I think all of the other ones are probably answered in one of my other sections. So if you're really itching for an answer to one of them, you can just go to the YouTube channel. I'm going to, I think I'm going to work backwards, skipping 9 because we covered that last week in recitation. Unless people have a concrete question that they like, an actual one that people want me to answer. Okay, cool. That's what I figured. So find the instantaneous rate of change of f of x is equal to x ln of x at x equal to e to the 3. So this is just saying plug in the e to the 3 for the derivative. So this is just a product rule. So it's first times derivative of the second plus the second times derivative of the first. So we just get 1 plus ln of x when we simplify things. And then we get f prime of e cubed is going to be equal to 1 plus ln of e cubed. And that's just 3 based on how ln is defined. So we get 1 plus 3 is equal to 4. Does that make sense? Cool. So the total revenue received from the sale of x items is given by r of x is equal, or is given by r of x, and the total cost to produce x items is given by c of x, where both functions are units in dollars. Find and interpret the marginal profit when 20 items are sold. So profit is revenue minus cost. So the marginal profit is the cost for producing one more item. So basically, it's asking us to find the derivative of this guy. So we want to set p prime of x. That's going to be equal to r prime of x minus c prime of x. So r prime of x is going to be equal to 60 divided by 2x plus 1. C of x is going to be equal to 1/2. So if we just set this guy equal to, so then we get the derivative of the profit is going to be equal to this right here. So find and interpret the marginal profit when 20 items are produced and sold. So p prime of 20 is going to be equal to 60 divided by 41 minus 1/2. So that tells me this right here is the profit, or this is roughly, this is the local linear estimation for the profit that I get from producing one more item when I am at 20. If I want to do the exact, then I would have to do P of 21 minus P of 20, but this is a local linear approximation that says, okay, based on the current slope of my profit function, this is how much I would expect to get for making one more item. Does that make sense? Cool. So, given simplified forms of the first and second derivatives, find of f of x is equal to 2x minus ln of 3x plus 1. Find the x coordinates of the critical points, determine the intervals where f of x is increasing and decreasing, and find the x coordinates of any points of relative extreme. So it's already done the derivative for us and actually simplified the derivative for us. So here, if I plug into this guy, so first off, are there domain restrictions on my first part? The answer is yes. 2x can be anything, but ln can only take in positive numbers. It tells me 3x plus 1 is greater than 0. If I rearrange this, I get x is greater than 1/3. That's strictly greater than 1/3. So the fact that this guy is not going to be defined at 1/3, sorry, negative 1/3. The fact that this guy is not going to be defined at negative 1/3 is not that big of a deal, because guess what? My function isn't defined there. So that tells me that the critical points are really the only thing that I have to worry about are where this guy is equal to 0 up top here. So that happens when x is equal to 1/6. That is going to be the point that breaks things. And then we get 9 divided by, so this guy is always positive. So if this guy is always positive, then that tells me that this is at 1/6, it's going to switch from decreasing to increasing, right? That's just a second derivative test. So 1/6, sorry, 1/6 f of 1/6. This is a local min, or I guess absolute min. And then we get, it's also a relative min, because it switches from decreasing to increasing, and that tells me that from negative 1/3, not inclusive, to 1/6, also not inclusive, it is decreasing. The function is decreasing. In other words, we have a negative derivative, and then from 1/6 to infinity, we have it is increasing, or we have a positive derivative. Does that make sense to people? Cool. So for each function below, find the x-coordinates of the critical points and determine the intervals on which f of x is increasing and decreasing. Find the x-coordinates of any points of relative extrema. So if this guy, if I do the first derivative of this x, then this is going to be equal to 12x squared plus 14x minus 20, right? I can pull a 2 out of this whole thing to simplify it a little bit, and then that gives me 2 times x squared plus 7x minus 20. And then you just, sorry, that should be 2 times 6x squared. To factor this, I would suggest using the quadratic equation and then you just plug in a test point on either side. I'm not going to, we've got a fair amount to cover in the next 15 minutes, so I'm not going to walk you through all those steps, but it shouldn't be anything super new. It's just, I would suggest using the quadratic equation for this one because it looked kind of messy to factor. If I were to do here, the first derivative, f prime of x would be equal to 5x to the fourth minus 20x cubed minus 60x squared. So that's going to be equal to, I can pull out a 5x squared from that, so 5x squared times x squared minus 4x minus 12. And I can factor this guy to x minus 6 and x plus 2 and 5x squared. So this right here is increasing. So now we have 3 regions that we want to check. And this one's actually pretty interesting because usually most things that you see, it jumps, goes positive, negative, positive, negative, positive, negative, or negative, positive, whatever it is. This guy is not going to be quite like that. And the reason is we have 2 zeros here. So it happens at x equals 0, x equals 6, and x equals negative 2. So this is a fairly interesting one. So we get negative infinity to negative 2, and then we get negative 2 to 0, and 0 to 6, and 6 to infinity. And we just plug in a test value in each of these ranges into the derivative to find out where it's increasing, where it's decreasing, and what our points are, what our critical points are. So if I plug in negative 10, then I would get what this becomes 5,000 plus, sorry, that's 50,000 plus 20,000 minus 6,000. So this is for negative 10. So that tells me this guy is going to be positive. If I plug in negative 1, then I get 5 minus, or sorry, plus 20 minus 60. So this is negative. So this is negative 1. That's my test case for this guy. If I plug in positive 1, then I get almost the same thing, but it's slightly worse for me. So it's 1 plus, sorry, minus 20 minus 60. So that is negative 75 is negative, and I get 6 to infinity. If I plug in positive 10, then I would get, what, 50,000 minus 20,000 minus 6,000. That's positive. So this is interesting because we don't normally get these things that are 2 negative intervals right next to each other. The reason we get it is because of this squared right here. If it was cubed, we would actually, if it's an even power, we'll get the same consecutive pattern. If it's an odd power, we will get the alternating pattern that we're used to. But so it's increasing from negative infinity to negative 2, union 6 to infinity, and then it's decreasing from negative 2 to 0, union 0 to 6. It's still not increasing at 0, so you can't do this as a single interval. You have to do it as the union of intervals. And that tells me that there is going to be, when you switch from positive, when you switch from increasing to decreasing, that tells me there's a max at negative 2, f of negative 2. And then there is a min at when you switch from decreasing to increasing at 6, f of 6. Right? Makes sense to everybody? Cool. I'll do C and then I'll move on. So x, so if I do the derivative of this guy, that's just a product rule. So it becomes first times the derivative of the second. The derivative of the second is -4 times e to the -4x times x plus the second times the derivative of the first. The derivative of the first is 1, so that's plus e to the -4x. So if I factor this, so this is f prime of x. If I factor this, I can get e to the -4x out, and I get 1 minus 4x. I set this equal to 0. I get x is equal to 1/4. So that is my only potential critical point. And now I would just plug in, this is defined for all x, so I would just plug in from -infinity to 1/4, and from 1/4 to infinity. The default, if possible, always plug it in, is 0, and in this case, if I plug in 0 to this equation, I get e to the 0 times 1 minus 0 is equal to 1, so it's positive. It's increasing on those bounds, and then it's going to be decreasing. If I plug in 1, then I get e to the -4 times 1 minus 4 times 1. That is equal to -3e to the -4. So this is decreasing. So increasing -infinity to 1/4, and decreasing 1/4 to infinity. Does that make sense to people? Cool. So find the equation of the tangent line of this graph. This, for the line, you need two things. You need a point and a slope. So a point, you just get the y value, the x naught comma y naught is equal to 1 comma f of 1. So that's 11 minus 1. So that's 11 minus 1. If I do f of 1 is equal to 11 minus 1 plus 4 times ln of 2 minus 1. Ln of 2 minus 1 is ln of 0 is 0. Or sorry, is ln of 1 is 0. Yeah, ln of 1 is 0. So this guy disappears, and then I just get 10. And then if I do the derivative of this guy, that is, so f prime of x, when I plug in f prime of 1, it's going to tell me the slope, and I just plug it into point slope form and rearrange it if you like. So f prime of x is going to be equal to -1 plus 4 times 2 divided by 2x minus 1. And if I plug in 1 here, I get is equal to -7. So f prime of 1 is going to be equal to -7. So if you then plug this guy in, you can just do y minus 10 is equal to -7 times x minus 1. So that becomes y is equal to -7x plus 3. So that right there, either of these forms is a correct way to write the line. But if it says point slope form, then it has to be the first one. If it says slope intercept form, then it has to be the second one. So this is just saying find the, so this is just saying literally what is n of 2 right here. So that's just saying how many students will have heard the rumor after 2 days is n of 2. So that's 1,000 minus, so sorry, times 1 times e to the -0.3. And then find and interpret the rate at which the number of students who heard the rumor is changing after 2 days. So this is just saying find n prime of 2. So if you do that, that is 1,000 times negative 1.5 negative 1.5 times negative e to the negative 1.5 t. So so that's n prime of t is equal to that, and then we can double positive this. Double negative becomes positive. So if you do that, and that's still point, then this becomes n prime of 2 is going to be equal to 150 times e to the negative 0.3, and then you would plug that in to this equation, right? Okay, so this is just saying, hey, I want to get the linear approximation of this guy and see how good that linear approximation actually is. And if I do that, then I get, so this guy right here is going to be roughly 111. This guy right here is going to be roughly 259. So this is saying that the n of t is going to be roughly equal to n of 2 plus n prime of 2 times t minus 2. So this is the line that we use to approximate it. And if we plug that in, we get n of t is going to be equal to n of 2 plus n prime of 2 times 3 minus 2. That's just 1. So that is equal to 259 plus 111. So that guy is going to be equal to, this should be a squiggly line, is going to be equal to 270, 370, which that's a pretty good estimate. 362 to 370 is not that big of a jump. So it's a pretty good estimate, but it's a linear approximation, so it's not going to be exact. Yeah, I will just do three of these guys kind of selected at random. So this guy right here is, this one right here is going to be just a basic chain rule. So we get 6 times 2x times 8 from the power here. That should be 8 from that power. And then we get x squared plus 4 to the 7. So the 2x is to the derivative of the inside. The 8 comes from the power. This guy is just the inside now knocked down to the power. So this is just the chain rule and the power rule. The same thing would go on here, except now we would also introduce a product rule, because we then have to do times that. This guy right here would be the quotient rule within a product rule. This right here is chain rule and quotient rule. So this guy is again a chain rule. It's probably the easiest way to do it. You can also split this up using also logs, but I think the easiest way to do it is just to do it as a chain rule. In that case, it goes to 40x cubed minus 21x squared plus 5 all over 10x to the 4th minus 7x cubed plus 5x. This guy, so e to the g of x, I should probably use h of x, goes to h prime of x e to the h of x. So I just do 5x to the 4th minus 36x squared, and then that is times e to the x to the 5 minus 12x cubed plus 8. And we are out of time, but most of the remainder of these guys are basically chain rule problems. Or like this guy's a product rule. This guy's a chain rule. But yeah. You guys are free, I suppose. If you have any other concrete questions, you can stick around and ask me, but you're free.
Thank you.
Have a good one.
Could you go over 5D, please?
5D in the worksheet or on this?
On the exam review.
Exam review. Okay, yeah, sure. So if I do the derivative of this, right? So I'm just going to actually rewrite this first as x plus 1 to the negative 1. So if I do the derivative of this becomes 4 times negative 1. The derivative of the inside is just 1, so that's not a very interesting chain rule. I guess it technically is a chain rule. Plus 1 to the negative 2. Okay, so that tells me that the only places where this can switch are where either this is equal to 0 or it's undefined. And guess what? It's undefined at the same point, but this guy is undefined at x is equal to 1, or sorry, negative 1. So here again, x cannot be equal to negative 1. If I plug that in, so that is actually going to be the point at which this guy switches from positive to negative. Sorry, no, not from positive to negative. That this guy switches. There's like a discontinuity of this. Basically looks something like this. And if I plug in either, so this, my interval, I guess, is defined. These are my two intervals where it's defined, and they're also going to be the two intervals that are divided by the potential switches from increasing to decreasing. So if I just plug in a value on either side, if I plug in 0, then I get negative 4 divided by 1 squared. So then this guy is positive, right? Sorry, it's negative 4 divided by positive. And then if I plug in, let's say negative 10, it's also going to be negative because I have negative 4 divided by some. This guy is always going to be positive because it's a square. So I have negative on top divided by positive. This is always going to be negative. So it's going to be decreasing on the interval negative infinity to negative 1, union negative 1 to infinity. It's not quite defined on the whole real line, so you can't write it as a single interval. And then there are no critical points. It just switches at a point where it's undefined. Does that make sense?
Yeah, thank you. And are there also no points of relative extremum then?
Yeah, there are no relative extrema.
Okay.
Yeah, the relative extrema can only be defined at the boundary, where this doesn't actually have a boundary. It's just not defined at a given point. And so these guys are open-ended, or at a critical point, and it doesn't have either of them.
Okay, thank you. Have a good day.
You too.